Good morning, ladies and gentlemen. I am Yukihiro Kato of Denso Corporation. I'm very honored to be here with you at ISSCC. You all know this image on the screen. This is a well-known QR code. This is how the code appears on my business card, along with my profile illustration. But did you know that QR code was invented by Denso? That's correct. Denso invented the QR code in 1994. This is one of many of our company's inventions. Today, I would like to share with you some others today. At first, let me introduce you to Denso Corporation. We became an independent company in 1949 after leaving Toyota Motor Corporation. Since that time, we have grown to become a leading supplier of automotive systems and components for major automakers. We have 150 associates in 200 group companies around the world, with sales of $40 billion. Importantly, we have devoted significant time, attention, and dollars to R&D, research and development. In fact, in 2016, 9% of all Denso's revenue went to R&D. Denso takes innovation seriously. In early hours, Denso made aggressive decision to set our company up for success, including an important technical cooperation agreement with Robert Bosch in 1953, and the establishment of Semiconductor Research Center in 1968. The Semiconductor Research Center is the origin of the in-house IC fabrication at Denso and the start of Denso semiconductor technology that today is one of the core competencies of our Densos. I have spent 30 years in the field of semiconductor at Denso, and I also have working in the field of connected vehicle and human-machine interfaces and automated driving technology for several years at Denso. As you know, automotive industry is immersed in a once-in-a-century transformation. At the core of transformation is focused on future mobility, specifically in three key areas: efficient driving by electrification, automated driving, and connected driving. First, let's explore efficient driving by electrification. As you can see here, electrification making progress. The reality is that DENSO has been working on electrification for a very long time. We have been contributing to the development of HEV and PHEV since the late 1990s. If you believe what you hear on TV or read the internet or in news articles, electrification is moving slowly. The reason for slow progress is that the massive changes are needed to accommodate the changing infrastructure for EV, and we still have several battery concerns, such as cost, battery charge capacity, and charging time, and recycling. If we consider eco-driving from well to wheel, which means total eco-analysis from oil field to fuel economy of vehicles, EV is not a perfect solution. All of our thermal power plants uses fossil fuel. A situation and the process cannot be changed easily. In our quest to solve some of these challenges, we have looked to other industries. Some of these electrification comes from railroad industry. Railroad industry has been able to improve the efficiency by replacing GTO, gate turn-off thyristor, power devices with IGBT, insulated gate bipolar transistor. Automotive inverter must be compact and lightweight, so we needed to reduce the size of inverter by increasing power density. Fortunately, with the help of consumer electronics and railroad technologies, power density of inverter has been increasing. Water cooling technology accelerates the progress. And dual-sided cooling and unified modules also improve the power density. We expect to see the more progress by silicon carbide, and I believe quantum structured gallium oxide has potential and will gain in popularity. We have lowered on resistance to shrink IGBT, which in turn enable unification of power module, and dual-side cooling has proven to be effective for downsizing of inverters. We call the power module the power cards because of its thin character, which is well suited for dual-side cooling. Silicon carbide has several excellent material properties, which makes it an ideal option for next generation of power devices. One challenge is that silicon carbide material is difficult to process, and its high crystal defect density has adverse effect on the yield of power MOSFET fabrication and quality. We can solve these issues with RAF method. RAF stands for repeated A phase. RAF method is excellent wafer growth process that dramatically reduces the defect density and enables power MOSFET fabrication. I'd like to show you RAF wafer growth process. So this is silicon carbide power MOSFET in 6-inch wafer. Next, let's take a look at automated driving. For automated driving to be successful, vehicle technology must recognize and assess multiple objects simultaneously and with high precision. Road intersections are always dangerous, even when humans are driving. Oh, sorry. What's happened? Oh, okay. Automated driving requires the technology that can detect multiple objects in a variety of conditions. Main components for recognition are cameras, which include image sensors, image processors, and microcomputers that calculate the output signal. The millimeter wave radars are used to detect objects in difficult conditions, such as complete darkness and dense fog. The lidars are well suited to accurately assess the distance. Oh. Let's compare human driving and automated driving. In automated driving, sensors replace our eyesight. Our brains are replaced by semiconductors with operation conducted by actuator. First, let's look at sense and recognition. I would like to show you the camera recognition example using our deep neural network hardware. The top image is input picture. The middle image is depth estimation. The bottom is semantic segmentation. This location is Akihabara in Tokyo, the holy land of anime. This location is always crowded. The camera with deep neural network hardware can identify the object pedestrian, automobile, roads, and so on. Next, let's go to judgment. For example, route calculation for path planning, which is an important yet difficult task for automated driving. What we found is that both CPUs and GPUs are not ideal solution for judgment of automated driving. CPUs are well suited to complex serial processing, but they are relatively slow. And although GPU can quickly perform large-scale parallel processing, they are not suitable for complex processing. Denso DFP is ideal for high-speed processing with the pace of natural human reflexes. GPU is good at attaining uniform work. On the other hand, DFP is good at mixed work. Because of variable border per calculation content and variable calculation scale, DFP provides exceptional processing without wasting time. DFP handles multiple processes simultaneously while consuming less than 1/10 of a GPU power and with speeds higher than a GPU. For route calculation, GPU analyzes all possible directions. With DFP, we can eliminate unnecessary paths and achieve a more efficient calculation. You can see that an added benefit of efficient DFP calculation is reduction of heat generation. So, last, let's go to the connected driving. We expect connected driving to deliver many excellent new services and values. Connected driving enhances driving support services, including mobility for elderly people, automated driving support, and traffic control capabilities. Connected driving also offers mobility services such as car sharing, ride sharing, multimodal mobility. In addition, connected driving offers convenient services, including paying car, efficient delivery, remote update, and failure prediction. If we consider side-by-side in connected driving, we know that number of connected vehicles increases, the computational time will explode. This is an example calculation results of combinations of vehicles and their many possible routes. How will we solve these issues created by explosion of computational time? with quantum computer. We are now planning demonstration of traffic control in Thailand using D-Wave quantum computer together with Toyota Tsusho Nexty Electronics. If we see physical side in connected driving, vehicle structure should follow dynamic evolution of connected vehicle services. Connected driving requires connected application. To facilitate this connected application, we must first activate plug-and-play function, similar to smartphones. Vehicle structure should support dynamic application installation even in the field, such as software update over the air, SOTA. Currently, application connection through a dedicated interface allows little flexibility. We have developed service bus control mechanism to facilitate application installation. By adopting service-oriented architecture, including service bus control and common interface, we can enable plug-and-play function. This, in turn, allows us to enjoy flexibility and several important services. As connected driving and automated driving become common, the importance of HMI will increase. The system becomes more complex. The information that the system provided will increase it. So, let's look at the Denso HMI. Oh, sorry. Okay. all information should be controlled by HMI ECU. Safety content is very important. It should be timely and robust. Safety content should never freeze, as we sometimes see with smartphones. This cannot happen in a vehicle, not even for 1 second. Adopting hypervisor, which is virtualization technology developed by IT industry for automotive application, enables the merging of robust OS for safety content and open OS. We will begin the mass production of our hypervisor SoC for HMI ECU next year. This new technology is a result of collaboration between Intel, BlackBerry, and Denso. What are the important takeaways today? First, information technology is essential for future mobility. Our challenge is solving the transition of information technology to automotive-grade application. Automotive-grade information technology will require quality, durability, functional safety, quick action, and maintenance services for lives of people and long-term use. Second, Denso is aggressively developing automotive-grade semiconductor technology and systems for the benefit of future mobility. I'd like to leave you with one final thought. To effectively continue our pursuit of new technologies and to ensure our long-term supply of parts and solutions, we need to increase long-term collaboration and partnership with IT companies and with semiconductor companies. This is critical to our long-range success. It was a pleasure to be here with you today. Thank you for your attention.